Hello. This quarter for our data science clinic project, we are working with the Building Decarbonization Coalition. I'm Andres, and here's our team, Andrew, Jared, and Victor. Here's a quick outline of our project for today. And we're going to start off with going over the overview of the project and BDC's problem. Just to start off, we want to quickly introduce our team. Our external mentors are Andre, Matt, Shrishti, Ria, and our internal mentor was Tatadisha, and our TA was Ian.
So first off, what is the BDC? The Building Decarbonization Coalition aligns critical stakeholders on a path to transform the nation's buildings through clean energy, policy research, and market development and public engagement. Their goal is to eliminate fossil fuels in buildings via the reinvention of commonly used carbon-powered heating and cooling systems, to improve people's health, cut climate change and air pollution, and ensure that our communities are more resilient to the impacts of climate change. They are currently mobilizing our nation's transition to renewable energy through the implementation of thermal energy networks. The BDC is revolutionizing the nation's heating and cooling systems, switching away from the current carbon-based, coal-powered standard. They are implementing geothermal HVAC systems to heat and cool buildings, campuses, and even neighborhoods at a time. You can heat a building's air or water via heat pump, improve the building's insulation with internal geothermal pipes, and more effectively implement rooftop solar panels. A more sophisticated solution prevails through TENS, or thermal energy networks, and when combined with heat pumps, can heat or cool multiple buildings at a time at extremely cost-effective prices. Thermal energy networks provide a superior alternative to traditional HVAC systems by expanding their scope and efficiency to operate at a larger scale. They produce no on-site emissions, consume much less energy than current energy heating and cooling technologies, and benefit from state and federal incentives for cost-effective adoption. They draw heat from diverse sources such as sewer water, data centers, refrigerated warehouses, and office buildings, creating a decentralized and sustainable energy model. TENS store energy in thermal reservoirs like bedrock, oceans, lakes, rivers, and water tanks, enabling efficient energy management. Heat sinks such as homes during winter, domestic hot water systems, and greenhouses ensure surplus energy is utilized effectively. TENS represents a scalable, interconnected system that maximizes resource efficiency and minimizes environmental impact. The implementation of TENS is still considered a novel technology. However, their potential to revolutionize energy consumption has led to the development of pilot projects across the entire country, primarily funded and supported by state governments. Private sector involvement, as seen by Meta and Google, suggests the growing demand for clean energy solutions capable of handling the electricity needs of large-scale data operations like data centers. Minnesota has taken a leading role in adopting networked geothermal solutions, supported by new legislation to modernize heating and cooling systems and to start achieving their own climate goals. Similarly, New York State is advancing with pilot projects for thermal energy networks, effectively implementing this technology citywide while generating valuable data to refine and scale its implementation. The goal of this project is to simplify access to reliable information on TENS for stakeholders, researchers, and community members. Currently, anyone seeking insights such as project timelines, ownership and funding details, or the environmental and consumer effects of these networks faces the challenge of navigating large, unorganized documents in the New York Department of Public Service database. This can be a time-consuming and frustrating process. To address this, the BDC has tasked us with developing a chatbot that makes finding information on TENS easier and more efficient. This chatbot allows users to ask questions and receive relevant answers generated by a language model, paired with the relevant sources for verification. This tool will reduce the complexity of data access, enabling the acceleration of implementing the renewable energy sources nationwide. The problem we're addressing is an engineering challenge: how to create a system that can answer industry-specific questions about thermal energy networks effectively. This solution requires combining multiple technologies to provide accurate real-time information. Our deliverables include a web scraper and word processor to clean documents retrieved from the NYDPS database, a RAG model to embed and store embeddings, and an LLM to create human-like responses using all relevant documents. Now, we'll address the engineering-based elements of this project. First, our word processing system extracts all documents related to TENS from the NYDPS database via web scraping and downloads them locally, ensuring all relevant data is easily accessible in our own directory. Second, we are using retrieval augmented generation, or RAG, to enhance the chatbot's ability to provide accurate, informative responses that will include supporting relevant documents. Third, the core of our solution will be an LLM capable of understanding natural language queries and generating factual, human-like responses. Finally, the end result will be an integrated command line interface chatbot capable of answering complex questions about TENS, complete with direct links to the underlying sources. The chatbot will make industry-specific information easy to access and navigate, addressing the needs of stakeholders, researchers, and community members. We begin by downloading PDFs from the NYDPS database using a web scraper. These documents are stored locally in our repository for further processing. To avoid duplicates, we store each file by its SHA hash because there are many repeated file names in the database. Next, we extract text from these PDFs, dividing the content into paragraphs. For tables within the PDFs, we convert them into textual format for easier integration into our pipeline. Once the text is extracted, we further process it by splitting it into sections and paragraphs. If a paragraph is too lengthy, for example, exceeding the token limit of the LLM we're using for response generation, we split it by sentence. Finally, we embed each paragraph with its associated metadata, such as the document title and other relevant attributes, ensuring that all processed text is structured and ready for the downstream tasks like querying or response generation.
And now I'm going to be talking about the RAG step of the process. At a high level, RAG is a method that retrieves the most relevant data to your question. So this means a user asks a query, which is compared against the database. At this level, it's important to remember that both the query and the data are matrices. The embeddings model's job is to code the information of the query and passage at a mathematical level. This is then used to find the most mathematically relevant passage. However, it's important to note that these embeddings still correspond to the actual passage. The original query and the relevant passages are then passed on to the LLM, which is then used to get the LLM to process the next stage of the process. Now to go over the response generation aspect of our system, we just talked about how the RAG step connects the query and the relevant passages together. You can see at the top, that's the bottom two parts. And we also add a system instruction template, which includes things like context for the model to understand how to answer the question and how to respond. This is important because we instruct the model by giving it the context necessary, the relevant text, and the original query we ask. This is passed on to the LLM, which ultimately gives us the response that answers the user's question. And we integrated all these parts together using two things. LangChain is an open source framework, which we use to build the applications, which we use to build the chatbot. And we put everything together using the command line interface, where the user can ask a question and get a specific answer within the terminal. And just to quickly kind of reinforce our work over the quarter, we have a diagram here which kind of depicts the three main parts. And the last part is putting everything together, as you can see. So at the first stage, we do the word processing, which includes things like documents like the doctrine or the statement of purpose for the organization. And then we embed those documents, and we also embed the query we're asking, which could be like, what is the BDC's mission? This is run through the RAG model, which will then give us the original query and the documents that are most relevant to the question. And you can see as we move to the right, that information is passed on to the LLM, which just to reinforce, it's the system prompt, it's the query, and it's the relevant documents that are being passed on to the LLM. And that allows us to get an answer like BDC's mission is to eliminate fossil fuels produced by buildings with the sources that we found the sun. And finally, we're going to talk about our results. So over the quarter, we finished the product that we outlined at the beginning, which is creating the chatbot. This was done with the word processing, the RAG model, the LLM model, and also at the last stage, integrating everything together, which allows us to make the final chatbot that people can actually interact with. And just to put this into context a bit, here's an actual example of the finished product. You can see at the top how the query is, can you use different documents to provide information on the implementation of TENS across New York City? And we asked this question because we wanted to kind of demonstrate the ability for the RAG model to look through different documents and say, hey, this paragraph here is most relevant, but we also found that this paragraph in another document is also really relevant. And this is really good because we are able to give the LLM a wide breadth of context it can use to answer the question, which you can look at to see how the LLM answered that as well. And just to kind of outline any future work that could be done in this project, we split it up in three parts. The word processing, it's good to always improve the accuracy of the processing for things like tables or footnotes, which are particularly tricky to process in the first place. And at the fine-tuning level, we have there's space to fine-tune the RAG and the LLM model to, I guess, further improve the accuracy of the retrieval, and also just to further improve the way the responses are phrased as well. And the last thing is to include additional hyperparameter to see if that results in more valuable responses as well. And that concludes our project. We just wanted to give a quick thank you to our mentors, Satadisha and Ian, for a good quarter. Thank you.